Hello, this is my video for Physics 2211 Lab 2, a motion of a falling object. Now, for the introduction to this lab, what we are doing is observing an object's motion falling downwards at a somewhat slowly speed, or a high FD magnitude, to where we can visualize the drag force in a short amount of time. Now, we will use this to examine an object that falls straight with gravity with the same mass, whilst examining the same object with said drag force as shown in the observed video. Now, understanding these results can help us lead to a better comprehension of drag force and how the drag force plus the Fg can lead to such terminal velocities in objects such as a ball of paper. In order to further understand both the observed data and the model position data, we need to state both the formulas and theories that are utilized the most in this experiment. Now, the velocity and position update formulas are most utilized for the model data, while the gravitational and drag force formulas are both used for the model data and for the real-life observed motion. Now, the theory that is most essentially related to all this is Newton's second law, which essentially states an object will accelerate in the direction of its F net force, which will further explain why an object will reach terminal velocity, where there is no F net. Now, we should now move to the tracker data, which will show our observed motion for. Now, for the observed data for our model, I took a video of myself dropping an empty paper towel tube down in my apartment floor about chest level. Now, in order to analyze this thoroughly and exact, I shifted the axis to where the paper towel roll falls directly down the axis, and I also used my height as a measurement of distance in order to accurately measure the distance of the paper towel roll falling. Now, as shown in the video, you can see the paper towel roll falling, and as I plotted manually all of the points, and also you can see the distance versus time graph here with the paper towel roll going down the negative axis, and the time versus distance graph over here, the distance in the y direction and time measured in seconds, distance measured in meters. Now, with this, we can finally get some initial data in order to use our model data in order to compare the two along with the observed experimental data. Now, as for the initial values that we're going to be used in our model glow strip data, we first have the mass, which I found using a scale, and we also have J hat, which can be found by observing that the paper towel roll only goes in the y direction. Now, for initial velocity, initial position, we can use that the initial velocity is going to be 0 as it's dropped from rest, and initial position based on the axis data that we got from tracker. We also can get time elapsed by the seconds in the table down in tracker. And finally, the b-value, which I specified here, but we utilize our model data in order to find this b-value later based on the terminal velocity of the data. Now, let's now transition over to our model data and our glow script data in order to observe these models. Clearly shown here, we can see some of the major coding changes that I made to the code, such as the velocity and position update formula I added to both, the initialization values which I added to both except for b, which I only added to the one with drag, the timing changes which I had with both, and the changes to net force which I only had for the first one, or the one without drag, gravity, and for the second one with drag, I had gravity along with drag force, so weight force and drag force. In order to compare the data, I put all three of the observed positions and times onto this graph right here. And some major conclusions we can get from this graph is that the experimental position without drag has a greater distance reached than both the experimental position with drag and the observed position. Another observation is that both the observed and experimental position with drag reach a point where there is linear progression rather than experimental, showing that there is some form of terminal velocity that is reached where there is constant negative position growth. Now, there's also that the observed and experimental with drag positions are shown to be very similar, yet the observed is slightly off. Now, in order to explain the slightly off position, the improvements to the data collection that can be shown is that the camera angle and was held very high and tilted, which we can fix by centering the camera to the middle of the motion, as well as holding it at a straight 90-degree angle, which would help the observed data. On another hand, the collection of mass was off because I used an inaccurate scale, so in order to ensure the mass is stable, we would use a more calibrated scale on the next experiment, which would help the experimental position with drag and without drag, as the gravity would be consistent with the observed position. In conclusion, we can finally answer the question about what models will predict this terminal velocity force, whether it be without or with drag. Now, the model with the drag force demonstrates the counteraction of forces of Fd and Fg, or drag force and gravitational force, will reach a certain, and where the velocity will reach a certain point where the Fd and the Fg will cancel each other out, resulting in a net force of 0 and a constant velocity, which is our terminal velocity as shown. Now, this is also shown in our experimental data as well. Now, for the what-if statement, if an object is thrown downward, would this reach the same terminal velocity steps? Now, in the video shown right here, I modified the data with drag force to show that even if you throw an object negative down, it will always still return to the same terminal velocity, as we can see here, to be right around negative 4.74 or negative 4.75, as shown right around here. And as you can see, the green arrow will reach an asymptote no matter where the velocity is initially, to where it will get to an F net force of 0. Thank you.